Welcome back to our series on microprocessors and microcontrollers. In our last video, we introduced the architecture of the microprocessor and highlighted its main functional blocks, the arithmetic and logic unit, the control unit, and the registers. Today, we're going to take a much closer look at these registers. Think of registers as the microprocessor's notepad, tiny high-speed storage locations inside the CPU that allow it to hold data, instructions, and results right where they're needed most. Without registers, the CPU would have to constantly fetch and store everything in external memory, which would slow down operations drastically. In this session, we'll carefully walk through the most important types of registers, understand how they operate, and see how they directly influence the way a program runs.
The accumulator register, A. The accumulator is one of the most frequently used registers inside the CPU. Its purpose is simple but vital. It temporarily stores data that will be used by the arithmetic and logic unit, or ALU, and it also holds the results after an operation is complete. Here's how it works. Imagine the CPU needs to add two numbers stored in memory. First, it loads the address of the first number into the memory address register, fetches the value, and places it into the accumulator. Next, it fetches the second number. The ALU then performs the addition using the accumulator's value as one of its inputs. The final result is placed back into the accumulator. This cycle means the accumulator is constantly being used, whether for addition, subtraction, logical comparisons, or even more complex operations. It's the heart of data processing inside the CPU, ensuring calculations happen quickly and results are ready for the next step. The status register, or flag register. After the ALU performs an operation, the CPU needs to know more than just the result. Was the result 0? Was it negative? Did it cause a carry or an overflow? These questions are answered by the status register, sometimes called the flag register. The status register is made up of individual bits, each representing a flag with a specific meaning. The Z flag, or 0 flag, is set if the result of an operation is 0. The N flag, or negative flag, is set if the result is negative. The C flag, or carry flag, is set if an arithmetic operation generates a carry beyond the word size. The V flag, or overflow flag, is set if the result exceeds the signed range of the microprocessor. The I flag, or interrupt flag, determines whether interrupts are currently ignored or processed normally. Let's take an example. If we add the hex numbers 02 and 06, the result is 08. Since it's not 0, the Z flag is reset. The result is positive, so N is also reset. There is no carry, so C is 0, and because the result fits comfortably within range, V is also 0. Now let's add F9 and 08. The result is 101. This time, the result is not 0, so Z is reset. It's still positive, so N is reset, but here we do have a carry, so the C flag is set. And once again, the result is within range, so V stays at 0. These flags are more than just indicators. They are often used in program control. For example, a program might repeat a loop until the Z flag is set, or branch to another instruction if the carry flag is active. This makes the status register an essential tool for decision-making within a microprocessor. The program counter or instruction pointer.
The program counter is like the microprocessor's internal GPS. It always contains the memory address of the next instruction to be executed. As the CPU fetches an instruction, the program counter is automatically incremented so that it points to the following instruction. This ensures instructions are carried out sequentially. However, if the CPU encounters a jump, branch, or call instruction, the program counter is updated with a new address, redirecting the flow of execution. Without the program counter, the CPU would have no idea where it is in a program or what to do next. It's the key to keeping program execution organized and continuous.
The Memory Address Register, or MAR. While the program counter decides which instruction to fetch, the Memory Address Register, or MAR, specifies where to fetch data or instructions from. When the CPU wants to read or write data in memory, it first places the target address into the MAR. The memory then uses this address to locate the correct data, which is transferred via the data bus. Let's return to our earlier addition example. The CPU first loads the MAR with the address of the first number. That number is then sent to the accumulator. Next, the MAR is updated with the address of the second number. After the addition is complete, the result can be stored back into memory, again at an address specified by the MAR.
The instruction register, also known as the IR, is another critical component of the CPU. Once the CPU fetches an instruction from memory, it cannot act on it immediately. Instead, the instruction is placed into the instruction register, or IR. The IR holds the current instruction while the CPU decodes it, preparing the control unit and ALU to execute it. Meanwhile, the program counter is incremented so that the CPU already knows where the next instruction is located. This process forms the fetch, decode, execute cycle, the heartbeat of every microprocessor. The IR ensures that the CPU never loses track of the current instruction, even while preparing for the next. General-purpose registers. Not all registers have specialized roles. Many microprocessors include general-purpose registers that can hold temporary data, addresses, or intermediate results. For example, the Intel 8085 microprocessor has 6 general-purpose registers: B, C, D, E, H, and L. These can be used independently as 8-bit registers or combined into pairs like BC, DE, or HL to form 16-bit registers. This flexibility allows programmers to optimize memory usage and perform more advanced operations. The Stack Pointer Register, SP, is another special-purpose register that plays a vital role in program execution. It keeps track of the top of the stack in RAM, a special memory region used for temporary storage. Whenever a subroutine or interrupt occurs, the CPU stores the return address, usually from the program counter, onto the stack. When the subroutine ends, the CPU retrieves this address from the stack, ensuring it returns to the correct point in the program. The stack pointer updates automatically whenever data is pushed onto the stack or popped from it. This allows the CPU to handle nested subroutines, recursive calls, and interrupts without confusion. And that brings us to the end of our deep dive into microprocessor registers. We've seen how each one plays a unique and indispensable role, from the accumulator handling arithmetic, to the status register reporting results, to the program counter guiding instruction flow, and the stack pointer managing subroutines. Together, they form the backbone of the CPU's ability to execute programs efficiently. We've now completed part 2 of our journey into the microprocessor, exploring the vital roles of its registers. In our next video, we'll bring these elements together by examining the fetch, decode, execute cycle. If you found this helpful, don't forget to subscribe to VisionaryTech and stay tuned for more lessons in our microprocessor and microcontroller series.